Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The chemistry required for life beyond Earth. Life at its most fundamental level is chemistry. Every thought you think, every breath you take, every movement you make results from chemical reactions occurring in your cells. Molecules bind together and break apart. Energy flows from one form to another. And through countless chemical transformations, inanimate matter becomes animate. Dead molecules become living organisms. Understanding what chemistry is required for life beyond Earth means understanding what makes life possible at all. The elements, the reactions, the solvents, and the energy sources that could allow chemistry to cross the threshold from complex but lifeless reactions into something that grows, reproduces, evolves, and ultimately builds civilizations among the stars. Carbon stands at the center of all known life. Every organism on Earth, from bacteria to blue whales, builds its body from carbon-based molecules. Carbon's unique properties make it extraordinarily suitable for life. Each carbon atom can form 4 chemical bonds with other atoms, allowing it to create an immense diversity of molecular structures, long chains, branching trees, rings, and complex 3-dimensional shapes. Carbon bonds with itself strongly enough to create stable molecules, but not so strongly that the bonds cannot be broken and rearranged through normal chemical reactions. This balance allows carbon molecules to be both stable enough to maintain structure and reactive enough to participate in the constant chemical transformations that life requires. Organic chemistry, the chemistry of carbon compounds, encompasses millions of known molecules and potentially billions more that could exist. Carbon combines readily with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create the molecules of life. Proteins, the workhorses of cells that catalyze reactions and build structures, are chains of amino acids linked together, each amino acid containing carbon, hydrogen, oxygen, and nitrogen. DNA and RNA, which store and transmit genetic information, are built from carbon-containing sugars, phosphate groups, and nitrogen-rich bases. Lipids, which form cell membranes and store energy, are long carbon chains with various functional groups attached. Carbohydrates, which provide energy and structural support, are carbon molecules with hydrogen and oxygen in specific ratios. But is carbon truly necessary for life, or is it simply the element that happened to work on Earth? Silicon, sitting directly below carbon in the periodic table, shares many of carbon's properties. Silicon also forms 4 chemical bonds and can create chains and rings similar to carbon. Science fiction has long speculated about silicon-based life, but silicon faces significant challenges. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains less stable. Silicon compounds tend to be much less diverse than carbon compounds. While carbon forms millions of different molecules, silicon chemistry is far more limited. Most critically, silicon's most common compound is silicon dioxide, quartz, sand, rock, which is extremely stable and insoluble. When silicon burns with oxygen, it creates solid rock rather than a gas that can be easily expelled and recycled. However, silicon-based life might be possible in environments completely unlike Earth. In extremely cold environments where water is frozen solid, silicon chemistry might become more favorable. In the presence of liquid hydrocarbons instead of water, silicon compounds might behave differently, remaining soluble and reactive rather than precipitating as rocks. A frigid world with seas of liquid methane or ethane, like Saturn's moon Titan, might provide conditions where silicon-based biochemistry could operate. Such life would function on completely different principles than Earth's carbon-based organisms, but it might still meet the basic requirements: complexity, self-replication, evolution, and metabolism. Hydrogen plays a crucial role in biochemistry beyond being part of organic molecules. Hydrogen ions, protons, are essential for energy generation in cells. Earth's organisms create differences in hydrogen ion concentration across membranes, then allow the ions to flow back through specialized proteins called ATP synthase, which harness the flowing ions to create ATP, the universal energy currency of life. This process, called chemiosmosis, powers nearly all life on Earth and represents a fundamental way of coupling energy sources to useful work. Any biochemistry, whether carbon-based or otherwise, would need some mechanism for capturing and storing energy, and hydrogen's simple chemistry makes it an excellent candidate for this role, regardless of the specific biochemistry involved. Oxygen serves multiple roles in Earth's biochemistry. It's part of water, part of most organic molecules, and it serves as the final electron acceptor in cellular respiration, the process by which organisms extract energy from food. When glucose is metabolized with oxygen, the reaction releases large amounts of energy that cells capture in the chemical bonds of ATP. This oxygen-based metabolism, called aerobic respiration, is far more efficient than metabolism without oxygen. However, oxygen was not always available on Earth. For the first 2 billion years or more, Earth's atmosphere contained very little free oxygen, and early life functioned without it, using anaerobic metabolism based on different chemical reactions. Some organisms today still live without oxygen, in deep ocean sediments or the guts of animals, using sulfur compounds, nitrates, or iron as alternatives to oxygen. Life beyond Earth might never develop oxygen-based metabolism if oxygen never becomes abundant in the atmosphere. Planets orbiting red dwarf stars might have difficulty accumulating oxygen because ultraviolet light from the star, which on Earth helps break apart water molecules in the upper atmosphere, leading to oxygen accumulation, is less intense. Life on such worlds might remain dependent on anaerobic metabolism indefinitely, which would likely limit the size and energy consumption of organisms. Active, energy-intensive lifestyles, like those of birds or mammals, require the high energy output that only oxygen metabolism provides. Alien life using alternative metabolic pathways might be restricted to smaller, slower, lower energy forms. Nitrogen is essential for proteins and nucleic acids. It's found in amino acids and in the bases that make up DNA and RNA. Nitrogen chemistry is complex and often difficult. Nitrogen gas in the atmosphere consists of 2 nitrogen atoms triple bonded together, making it very stable and unreactive. Converting atmospheric nitrogen into biologically useful forms, a process called nitrogen fixation, requires significant energy or specialized catalysts. On Earth, certain bacteria can fix nitrogen using enzymes containing iron and molybdenum. Lightning also fixes nitrogen by forcing nitrogen and oxygen to react in the high-energy conditions of electrical discharge. Life on other planets would need some source of biologically available nitrogen, either through similar fixation processes or through nitrogen already present in reactive forms. Phosphorus plays a unique and critical role in biochemistry. It's part of the backbone of DNA and RNA, linking the sugar molecules together into the long chains that store genetic information. It's also central to ATP, the molecule that stores and transfers energy in cells. Phosphate groups can be added to and removed from molecules to regulate their activity, serving as switches that turn cellular processes on and off. There is no obvious substitute for phosphorus in these roles. Unlike carbon, nitrogen, and oxygen, which are abundant in the universe, phosphorus is relatively rare, created only in certain types of stellar processes. A planet poor in phosphorus might struggle to develop complex life, at least of the kind we would recognize. Sulfur contributes to protein structure through disulfide bonds, connections between sulfur atoms in different parts of a protein that help the protein fold into its proper three-dimensional shape. Some organisms use sulfur compounds in their metabolism instead of or in addition to oxygen. Near hydrothermal vents on Earth's ocean floor, bacteria oxidize hydrogen sulfide, the compound that smells like rotten eggs, to generate energy. Entire ecosystems build on these chemosynthetic bacteria, demonstrating that sunlight and photosynthesis are not necessary for life. An alien world with extensive volcanic or hydrothermal activity could support life based on sulfur chemistry, even in complete darkness. Trace elements, though needed in tiny amounts, are essential for many biological processes. Iron is central to hemoglobin, the protein that carries oxygen in blood, and to many enzymes involved in energy metabolism. Magnesium sits at the center of chlorophyll molecules, enabling photosynthesis. Zinc, copper, manganese, and other metals serve as cofactors for enzymes, helping catalyze reactions that would otherwise proceed too slowly to sustain life. An alien biochemistry would likely require its own set of trace elements, perhaps using metals common on its world but rare on Earth, or finding entirely different solutions to catalysis and molecular structure. Water serves as the solvent for biochemistry on Earth, the medium in which all cellular chemistry occurs. Water has remarkable properties that make it ideal for life. It remains liquid across a wide temperature range, from 0 to 100 degrees Celsius at Earth's atmospheric pressure. It has a high heat capacity, meaning it resists temperature changes, which helps organisms maintain stable internal temperatures. Water molecules are polar, with a slight positive charge on one end and a slight negative charge on the other, allowing water to dissolve ionic compounds and interact with many different types of molecules. The hydrogen bonds between water molecules create surface tension, capillary action, and the unusual property that ice floats on liquid water, a characteristic that has profound implications for life in oceans and lakes. But is water necessary for life, or might other liquids serve as solvents for alternative biochemistries? Ammonia has been proposed as a possible alternative. Ammonia remains liquid at much colder temperatures than water. It freezes at -78 degrees Celsius and boils at -33 degrees Celsius at Earth's atmospheric pressure. A very cold planet, too cold for liquid water, might have lakes or oceans of liquid ammonia. Ammonia shares some of water's properties. It's polar, can form hydrogen bonds, and dissolves many substances. However, ammonia is a less effective solvent than water for many compounds, and the biochemistry that could operate in liquid ammonia would necessarily be very different from Earth's water-based life. Methane and ethane, though non-polar and very different from water, exist as liquids on Titan, Saturn's largest moon. Titan has lakes and rivers of liquid hydrocarbons on its surface, creating a hydrological cycle remarkably similar to Earth's water cycle, but operating at temperatures around -180 degrees Celsius. Could life exist in these hydrocarbon lakes? The chemistry would be completely unlike anything on Earth. Reactions that occur readily in water might not occur at all in methane, while entirely different reactions become possible. Cell membranes would need to be built from different molecules. The lipid membranes used by Earth cells wouldn't function in liquid methane. Energy metabolism would follow different pathways. But some scientists argue that the sheer strangeness of Titan's environment doesn't preclude life, only life that operates on unfamiliar principles. Supercritical fluids represent another possibility. Under high pressure and high temperature, substances enter a supercritical state where the distinction between liquid and gas breaks down. Supercritical carbon dioxide, for instance, behaves as both liquid and gas simultaneously, with properties of each. Deep beneath the surfaces of certain planets, conditions might create supercritical water or other supercritical fluids that could potentially serve as solvents for exotic biochemistries operating under extreme conditions. Energy sources drive all biochemistry. On Earth, sunlight powers most ecosystems through photosynthesis. Plants and photosynthetic bacteria capture light energy and use it to build organic molecules from carbon dioxide and water. These organic molecules then flow through food chains, ultimately providing energy for all other organisms. But many alternative energy sources exist. Chemical energy from redox reactions, where electrons transfer from one molecule to another, can sustain life in complete darkness. Radioactive decay in a planet's interior could provide steady energy through the heat it generates, potentially supporting life in subsurface environments for billions of years, even if the star above has long since died. The origin of life, the transition from complex chemistry to living organisms, requires conditions where organic molecules can form, concentrate, and begin the process of self-replication and evolution. On Earth, this might have occurred in tidal pools, in hydrothermal vents, in ice, or even in the atmosphere. The exact location and mechanism remain uncertain, but the chemistry required involves forming increasingly complex molecules from simpler precursors, eventually creating molecules capable of catalyzing reactions, including their own replication. This requires an energy source to drive uphill reactions that create complexity from simplicity, fighting against entropy. It requires some form of containment, membranes or surfaces, to concentrate molecules and create distinct chemical environments. And it requires time for random chemical processes to explore countless possibilities until self-replicating systems emerge. The universality of certain chemical principles suggests that life elsewhere, no matter how alien, would still obey the same rules of chemistry and thermodynamics that govern Earth's life. All life must extract energy from its environment and use that energy to create and maintain complex organization. All life must reproduce, passing information to offspring. All life must evolve through variation and selection. These requirements constrain the chemistry of life, regardless of what specific molecules are involved. Carbon is not the only possible basis for complex chemistry, water is not the only possible solvent, and oxygen is not the only possible energy source, but any living system must solve the same fundamental chemical problems: how to capture and store energy, how to build complex molecules, how to replicate information, and how to maintain organization in a universe that constantly tends toward disorder. The chemistry required for life beyond Earth encompasses the familiar carbon, water, proteins, and DNA, and the exotic silicon biochemistry in hydrocarbon seas, life in supercritical fluids, using metals we've never heard of, organisms metabolizing on reactions we've never imagined. The universe provides the raw materials everywhere: hydrogen from the Big Bang, heavier elements forged in stars and scattered through supernova explosions. Every planet, moon, and asteroid contains chemistry, happening constantly through radiation, temperature gradients, and the simple mixing of different compounds. Whether that chemistry crosses the threshold into life depends on having the right combination of elements, solvents, energy sources, and time, ingredients that might exist on countless worlds throughout the cosmos, waiting for chemistry to become biology in endless variations on the theme of life. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival: in boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond. In volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences, and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of Baraful's pressure-loving organisms suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environment can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The lighthouse stars that spin incredibly fast. In 1967, a graduate student named Jocelyn Bell noticed something peculiar in her radio telescope data, a signal that pulsed with extraordinary regularity, repeating every 1.3373 seconds. The precision was so remarkable that she and her advisor initially wondered whether they had detected an artificial signal from an extraterrestrial civilization. They jokingly called it LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, each with its own precise period, it became clear they were witnessing something natural, but entirely unexpected. Rapidly spinning neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. These objects, now called pulsars, are among the most extreme objects in the universe. They are neutron stars, the collapsed cores of massive stars that exploded as supernova, compressed to densities where a sugar cube-sized amount of material would weigh as much as a mountain. What makes pulsars special is not just their incredible density, but their rotation. These stars spin at rates that seem impossible for something so massive. Many complete one rotation in less than a second, some in mere milliseconds, whirling around hundreds of times per second while containing more mass than the Sun. The story of a pulsar begins with the death of a massive star. When a star, at least 8 times more massive than the Sun, exhausts its nuclear fuel, its core collapses catastrophically. The outer layers rebound and explode outward as a supernova, but the core continues collapsing until nuclear forces halt the compression, creating a neutron star about 12 miles across. This neutron star inherits the angular momentum of the original star's core, but because the radius has shrunk by a factor of perhaps 100,000, the rotation rate increases dramatically through conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, rotating faster and faster as their radius decreases. The collapsing stellar core undergoes the same process, but on a far more extreme scale. A star that was rotating once every few weeks might produce a neutron star that rotates several times per second. The fastest spinning pulsar known, designated P-SRJ 1748-2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the neutron star is ablate, bulging significantly at its equator due to centrifugal forces, yet it holds together through the tremendous strength of neutron degenerate matter and its own crushing gravity. The lighthouse effect that makes pulsars detectable comes from their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe, typically 1 trillion times stronger than Earth's magnetic field. When the core of the parent star collapses, any magnetic field present is compressed and amplified tremendously. This field doesn't simply shrink, it gets concentrated into a much smaller volume, intensifying to values that would tear apart atoms and polarize the vacuum of space itself. This intense magnetic field is not aligned with the neutron star's rotation axis. Just as Earth's magnetic poles don't coincide with its geographic poles, a neutron star's magnetic axis is typically tilted relative to its spin axis. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines, particularly near the magnetic poles. These particles, accelerating at relativistic speeds, emit intense beams of radiation through a process called synchrotron radiation. The beams emerge from the magnetic poles, creating two searchlights that sweep through space as the neutron star rotates. When one of these beams sweeps across Earth, we detect a pulse of radio waves, X-rays, or gamma rays, depending on the pulsar's characteristics. The pulse arrives with extraordinary regularity. The best pulsars keep time as accurately as atomic clocks, varying by only microseconds over years. This precision exists because the neutron star is such a stable rotator. Its enormous rotational inertia, combined with its extreme density and rigidity, means that nothing can easily change its spin rate. It's like an enormous cosmic flywheel, storing vast amounts of rotational energy and releasing it only very gradually. The radio emission mechanism is complex and still not completely understood, despite decades of study. The acceleration of charged particles near the magnetic poles creates a cascade of electromagnetic radiation. These particles follow the curved magnetic field lines, and as they accelerate, they emit photons. These photons can interact with the intense magnetic field to create more particle-antiparticle pairs, which then accelerate and create more photons, building up a cascade that produces the intense radio emission we detect. The region where this occurs, just above the magnetic poles, is called the polar cap, and it's here that the lighthouse beams originate. Not all pulsars emit at the same wavelengths. Some are primarily radio pulsars, detected through their radio emission. Others are X-ray pulsars, emitting primarily high-energy X-rays. A few emit gamma rays, the most energetic form of electromagnetic radiation. Some pulsars emit across the entire electromagnetic spectrum simultaneously, creating pulses detectable from radio waves through gamma rays. The emission properties depend on factors like the neutron star's age, its magnetic field strength, its rotation rate, and the environment surrounding it. Young pulsars, recently formed in supernova explosions, tend to rotate faster and have stronger magnetic fields than old pulsars. The Crab pulsar, formed in a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and emits powerfully across the electromagnetic spectrum. It sits at the center of the Crab Nebula, the expanding remnant of that supernova explosion, and its intense radiation illuminates the surrounding nebula, causing it to glow. The pulsar acts like a cosmic power station, converting its rotational energy into electromagnetic radiation and high-energy particles that energize the nebula. Pulsars slow down over time, gradually losing rotational energy. This spin-down occurs because the rotating magnetic field acts like a brake. The magnetic field lines extend far into space, and as they rotate with the neutron star, they drag charged particles along, accelerating them and carrying away energy and angular momentum. This magnetic braking gradually robs the neutron star of its rotational energy. A young pulsar might slow down measurably over just a few years, while an old pulsar might take millions of years to show detectable changes in its period. The rate at which a pulsar slows down reveals information about its magnetic field strength and age. By measuring the current rotation period and the rate of change of that period, astronomers can estimate how long the pulsar has been spinning down and how much longer it will continue to pulse before its rotation becomes too slow and its magnetic field too weak to generate detectable radiation. Most pulsars have lifetimes of tens of millions of years as active radio sources before they fade from detectability, though the neutron star itself continues existing and spinning, just no longer producing observable pulses. Some pulsars experience sudden speed-ups, called glitches. The neutron star's rotation rate, which normally decreases steadily, suddenly increases slightly, then resumes its gradual slowdown. These glitches are thought to occur because the neutron star's interior contains a superfluid, a state of matter with zero viscosity that can flow without any resistance. This superfluid rotates faster than the star's crust, and occasionally, angular momentum transfers suddenly from the superfluid to the crust, causing the observable spin-up. Glitches provide rare windows into the exotic physics occurring inside neutron stars, where matter exists in states impossible to recreate in laboratories. Millisecond pulsars present a fascinating puzzle. These pulsars rotate hundreds of times per second, far faster than young pulsars, yet they're old neutron stars, billions of years old. How can an old pulsar be spinning so fast? The answer lies in a process called recycling. A millisecond pulsar was once a normal pulsar that slowed down over hundreds of millions of years. But if it's in a binary system with a companion star, and that companion evolves to become a giant star, matter can flow from the companion onto the neutron star. This infalling matter carries angular momentum, spinning up the neutron star like water hitting a water wheel. Over millions of years, the neutron star is spun up to millisecond periods, recycled into a new youth of rapid rotation. Some pulsars are part of binary systems where we can directly observe this process happening. X-ray binary pulsars show X-ray pulses as the neutron star accretes material from its companion. The infalling material, heated to millions of degrees before hitting the neutron star's surface, emits intense X-rays. These systems are the evolutionary precursors to millisecond pulsars, caught in the act of being spun up by accretion. The most rapidly rotating pulsars ever discovered are all millisecond pulsars, and some of them are in dense globular clusters where stars are packed closely together. The high stellar density in these clusters makes binary interactions more likely, creating environments where many neutron stars can be recycled through accretion. Some globular clusters contain dozens of millisecond pulsars, creating a cosmic percussion section where numerous neutron stars pulse at different rates, each one a precisely ticking clock with its own unique period. Pulsars can also have planets. The first exoplanets ever discovered orbit a pulsar called PSRB 1257+12. These planets were detected through tiny variations in the pulsar's timing. As the planets orbit, their gravity tugs the pulsar slightly back and forth, causing the pulses to arrive slightly early or late in a periodic pattern. The planets orbiting this pulsar are thought to be second-generation worlds, formed from the debris of the supernova explosion that created the neutron star, or possibly from material that later fell back onto the system. These are harsh worlds, bathed in intense radiation from the pulsar, utterly unlike the planets orbiting normal stars. Binary pulsars, where two neutron stars orbit each other, provide extraordinary laboratories for testing general relativity. The orbital motion of such systems produces gravitational waves that carry away energy, causing the orbit to shrink over time. The rate of orbital decay matches Einstein's predictions with incredible precision. The first binary pulsar discovered, PSRB 1913+16, provided the first indirect evidence for gravitational waves. Decades before, gravitational wave detectors directly observed them from merging black holes and neutron stars. The regularity of pulsar timing has practical applications. Astronomers use networks of millisecond pulsars across the galaxy as a cosmic timing array, watching for tiny correlated deviations in their pulse arrival times that would indicate gravitational waves passing through the galaxy. These pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially detecting the gravitational wave background from supermassive black hole mergers throughout the universe. Pulsars also serve as natural laboratories for extreme physics. The conditions near their surfaces, intense magnetic fields, extreme gravity, densities exceeding that of atomic nuclei, cannot be reproduced on Earth. By observing pulsars across the electromagnetic spectrum and measuring their properties precisely, physicists learn about how matter behaves under conditions that push the boundaries of our physical theories, testing general relativity in strong gravitational fields and probing the equation of state of matter at nuclear densities. These spinning neutron stars, these cosmic lighthouses flashing their beams across the universe, represent one endpoint of stellar evolution. From the violent collapse of a massive star's core emerges an object so dense, so rapidly spinning, so strongly magnetized that it challenges our understanding of physics. Each pulse detected from a pulsar is a message from one of the universe's most extreme environments, a precisely timed signal carrying information about physics at the edge of what's possible, reminding us that the universe contains objects and phenomena far stranger than we could have imagined before we discovered these remarkable, spinning stellar remnants. The universal laws that would shape all life. While alien life might look nothing like Earth's organisms, using different chemistry, different genetic molecules, different metabolic pathways, certain fundamental principles would constrain and shape all life everywhere in the universe. These universal laws arise not from biological specifics, but from physics, chemistry, thermodynamics, and information theory, disciplines that operate identically throughout the cosmos. Understanding these universal constraints reveals what all life, no matter how alien, must have in common, and what fundamental challenges every living system must solve to exist, grow, reproduce, and evolve on any world, under any star, in any galaxy. The laws of thermodynamics govern all physical processes, and life is no exception. The second law of thermodynamics states that entropy, disorder, tends to increase in closed systems. Left to themselves, organized structures break down, concentrated energy disperses, and order gives way to chaos. A sandcastle erodes, a hot cup of coffee cools to room temperature. Complex molecules break apart into simpler ones. This universal tendency toward disorder creates life's fundamental challenge. Living organisms are highly organized, low-entropy systems existing in a universe that constantly pushes toward disorder. Maintaining biological organization requires constant energy input to fight against entropy's relentless pull. All life, everywhere in the universe, must extract energy from its environment and use that energy to maintain and build ordered structures. On Earth, photosynthetic organisms capture energy from sunlight. Other organisms obtain energy by consuming and metabolizing food, breaking down the chemical bonds in organic molecules and harnessing the released energy. Chemosynthetic organisms extract energy from inorganic chemical reactions. The specific mechanisms vary enormously, but the underlying requirement is universal. Every living thing must have a metabolism, some way of extracting usable energy from its surroundings to power the processes that maintain life. This creates a fundamental constraint. Life can only exist where energy flows. Environments in perfect thermodynamic equilibrium, where no energy gradients exist, cannot support life. Life requires disequilibrium, a hot vent and cold water, sunlight falling on chemical systems, redox gradients between different chemical species. These disequilibria provide the energy flow that life harnesses. Alien life, no matter what chemistry it uses or what planet it inhabits, must exist in regions where energy flows from higher to lower energy states, capturing some of that flowing energy to power metabolism. Evolution through natural selection represents another universal principle. Any system capable of reproduction, variation, and selection will inevitably evolve. This is not a biological principle, but a logical and mathematical necessity. If organisms reproduce, creating copies of themselves, and if those copies are not perfect but contain variations, and if some variants survive and reproduce more successfully than others due to those variations, then the population will change over generations as successful variants become more common and unsuccessful variants decline. This is evolution by natural selection, and it operates on any replicating system with heritable variation subject to selection pressures. Alien life would therefore inevitably evolve, becoming adapted to its environment through countless generations of selection favouring organisms better suited to local conditions. The specific adaptations would differ. Alien organisms might evolve features we've never imagined, but the process would be the same. Evolution is not optional or unique to Earth. It's a fundamental consequence of how replicating systems behave over time. Any civilization that discovers alien life would find that life has been shaped by evolution just as Earth's life has been shaped, even if the resulting organisms look and function completely differently. This evolutionary principle creates a corollary, convergent evolution, where different lineages independently evolve similar solutions to similar problems, occurs because physics and chemistry constrain the possible solutions. Eyes evolved independently many times on Earth because detecting light provides such valuable information, and focusing light onto photosensitive cells is the most effective way to create detailed images. Streamlined body shapes evolved independently in fish, dolphins, ichthyosaurs, and penguins because that shape minimizes drag in water. These convergences occur because physical laws determine what works well in given circumstances. Alien life would show similar convergences. Any organism that needs to move through fluid efficiently would likely evolve some form of streamlined shape because physics demands it. Any organism that needs to detect electromagnetic radiation would likely evolve some structure that captures and focuses that radiation. The details would vary. Alien eyes might have 10 light-sensing structures instead of 2, might sense infrared instead of visible light, might use completely different photosensitive molecules than Earth organisms. But the basic function would be similar because the physics of light detection operates universally. Information storage and transmission represent another universal requirement. Living organisms must store information about how to build and maintain themselves, and they must transmit this information to their offspring. On Earth, this information is stored in DNA and RNA sequences, but the specific molecule doesn't matter. What matters is that some physical system must encode instructions that can be copied and passed to the next generation, and these instructions must contain enough information to specify the organism's structure and function with sufficient detail that offspring resemble parents. The amount of information required sets minimum limits on the complexity of genetic systems. A viable organism cannot be specified by just a few bits of information. It requires substantial information content to encode even the simplest metabolic pathways, structural components, and reproduction mechanisms. Earth's simplest free-living bacteria have genomes containing roughly 500,000 base pairs, encoding about 500 genes. This represents the approximate minimum information content for independent life under Earth conditions. Alien life might require more or less information, depending on environmental complexity and metabolic strategies, but some minimum threshold exists below which organisms cannot encode enough instructions to function and reproduce reliably. The fidelity of information copying, how accurately genetic information is replicated, creates a universal trade-off. Perfect copying with zero errors would prevent evolution because no variation would arise. But too many copying errors would lead to error catastrophe, where genetic information degrades faster than selection can eliminate harmful mutations. There exists an optimal error rate that balances stability and evolvability, allowing organisms to maintain essential functions while still generating the variation necessary for adaptation. Alien genetic systems would face this same trade-off and would likely evolve error rates in a similar optimal range, regardless of what molecules store their genetic information. Physical scaling laws constrain organism size and structure. The strength of materials scales with cross-sectional area, proportional to the square of linear dimensions, while weight scales with volume, proportional to the cube of linear dimensions. This means that, as organisms get larger, their weight increases faster than their structural strength. A human scaled up to 10 times normal height would weigh 1,000 times as much, but would have bones only 100 times as strong. The skeleton would collapse under the weight. This scaling law explains why large land animals have thick, sturdy legs relative to their body size, while small animals have gracile limbs. Elephants have legs like pillars. Mice have delicate, thin legs. An alien planet with higher gravity would have organisms with even thicker, stronger structural supports relative to their size. A lower gravity planet would allow more slender structures. But the mathematics of scaling operates universally, constraining what body plans are physically possible at different sizes. Surface area to volume ratio creates another universal constraint. Small organisms have large surface area relative to their volume, making heat loss rapid and making diffusion effective for transporting materials. Large organisms have small surface area relative to volume, retaining heat more effectively but requiring specialized circulatory systems because diffusion becomes inadequate for transporting nutrients and waste across large distances. These scaling relationships would govern alien life just as they govern Earth life, determining which transport mechanisms are necessary at different sizes and what thermal regulation strategies are required. Chemical reaction rates depend on temperature, creating universal constraints on metabolism. Higher temperatures speed up chemical reactions exponentially. A rule of thumb is that reactions roughly double in rate for every 10-degree increase in temperature. This means organisms in hot environments can have faster metabolisms, grow more quickly, and potentially think faster if they're intelligent. Organisms in cold environments have slower metabolisms, grow more slowly, and would process information more slowly if conscious. These temperature effects on reaction kinetics are universal, affecting any chemistry-based life regardless of specific biochemistry. Diffusion rates determined by physics limit how large cells can be. Molecules move through cells by random thermal motion, diffusion. This process is slow. A molecule might take seconds or minutes to diffuse across a large cell. This limits cell size because cells need to move nutrients, wastes and signals around internally, and diffusion becomes prohibitively slow beyond certain sizes. Earth's largest cells are only about 1 millimeter across, and most are much smaller. Alien cells, regardless of their chemistry, would face similar diffusion limits unless they evolved active transport mechanisms, like Earth's eukaryotic cells use, with molecular motors moving cargo along cellular highways. The speed of light creates absolute limits on information transfer. No signal can travel faster than light, which means there are minimum response times for any organism based on its size. An organism the size of a bacterium, a few micrometers, experiences internal light travel times of trillionths of a second, essentially instantaneous. But a hypothetical, planet-sized organism would experience light travel times of tens of milliseconds from one side to the other, creating unavoidable delays in communication and coordination between distant parts. Very large organisms would necessarily be slow to respond to stimuli and might need decentralized control systems because centralized coordination becomes impractical when signal delays become significant. Energy efficiency sets ultimate limits on what metabolic processes are possible. Chemical reactions have maximum energy yields determined by the bonds being broken and formed. An organism cannot extract more energy from a reaction than the chemistry allows. This means life on worlds with limited energy availability, dim stars, deep subsurface environments, chemical poor conditions would necessarily have low energy lifestyles, growing slowly and reproducing infrequently. High energy environments allow active, energetic lifestyles, but also demand mechanisms to dissipate excess heat. Water's unique properties, while not absolutely required for life, make it an excellent solvent for biochemistry. Water remains liquid across a convenient temperature range, has high heat capacity that buffers against temperature changes, expands when freezing so ice floats, acts as a polar solvent that dissolves ions and many organic molecules, and participates in many biochemical reactions. While life could potentially use other solvents, liquid ammonia, methane, supercritical carbon dioxide, any solvent must have properties that allow complex chemistry to occur, molecules to dissolve and interact, and cellular compartments to form. Not many liquids have the right combination of properties, making water-based life probably more common than exotic alternatives, though not exclusively so. Complexity emerges hierarchically, with simple components combining into more complex structures, which combine into still more complex systems. Atoms form molecules. Molecules form macromolecules. Macromolecules form cellular structures. Cells form tissues. Tissues form organs. Organs form organisms. Organisms form ecosystems. This hierarchical organization seems to be how complexity arises universally, because building complex systems directly from simple components becomes unmanageable beyond certain complexity levels. Modular hierarchical construction allows greater complexity to be achieved and maintained. Alien life would likely show similar hierarchical organization, even if the specific components at each level differ completely from Earth's biological hierarchy. Darwinian selection favors efficiency. Organisms that use resources more efficiently have advantages over wasteful competitors. This drives evolution toward optimized solutions within physical constraints. Alien life would similarly be shaped by selection for efficiency, though what constitutes efficient depends on environmental context. In energy-rich environments, speed might matter more than efficiency. In energy-poor environments, extreme efficiency becomes essential for survival. But the general principle that natural selection tends to optimize organisms for their specific circumstances within physical constraints operates universally. The universal laws that would shape all life, encompass thermodynamics, demanding that life exist only where energy flows, and that organisms extract energy to maintain order against entropy. Evolution, through natural selection, being an inevitable consequence of imperfect replication with variation. Information requirements, setting minimum complexity thresholds, scaling laws constraining size and structure, chemical kinetics determining metabolic rates, and physical limits on signal speeds, and diffusion rates imposing fundamental constraints on how large and fast organisms can be. These laws operate identically throughout the universe, guaranteeing that while alien life might look and function completely differently from Earth's organisms in countless details, the fundamental principles governing life's existence, evolution, and physical limitations would be the same everywhere, creating a common framework that all life must operate within, regardless of whether it's based on carbon or silicon, DNA or something entirely different, oxygen metabolism or sulfur chemistry. Because physics and chemistry and thermodynamics and information theory operate identically on every world orbiting every star in every galaxy, creating universal constraints that shape all possible forms of life into entities that must harvest energy, maintain organization, store and transmit information, and evolve through selection, making these principles the true universals of biology that would apply to any living thing humans might ever encounter. How galaxies live and die. Galaxies are not eternal, unchanging structures frozen in the void. They are dynamic systems that evolve over billions of years, passing through distinct phases from birth to maturity to eventual decline. Each galaxy follows a life story shaped by gravity, star formation, gas flows, and violent interactions with other galaxies, ultimately transforming from active star-forming systems into quiet collections of aging stars, or sometimes meeting more dramatic fates in collisions that tear them apart and rebuild them into something new. The birth of a galaxy begins in the early universe, just a few 100 million years after the Big Bang. At this time, the cosmos was filled with vast clouds of hydrogen and helium, distributed nearly uniformly, but with tiny variations in density imprinted during the first moments after the Big Bang. Dark matter, invisible but gravitationally powerful, began to collapse first into clumps and filaments, creating gravitational wells that attracted normal matter. Gas flowed along these dark matter filaments, accumulating in regions where the gravitational pull was strongest. These early accumulations of gas were turbulent, chaotic places. The gas was cold, collapsing under its own gravity into smaller and smaller clumps. Within these collapsing clouds, the first stars ignited, massive and brilliant, burning through their nuclear fuel in just a few million years before exploding as supernova. These explosions enriched the surrounding gas with heavier elements, carbon, oxygen, iron, and others, that hadn't existed in the primordial universe. More stars formed from this enriched gas, creating a positive feedback cycle where star formation bred more star formation. A young galaxy is a vigorous place, forming stars at prodigious rates. Gas continues to fall into the galaxy from the surrounding cosmic web, providing fresh fuel for star formation. These early galaxies are often irregular in shape, lacking the elegant spiral arms or smooth elliptical forms of mature galaxies. They're clumpy and asymmetric, filled with giant regions of intense star formation where thousands of stars are being born simultaneously. The massive stars in these regions produce copious ultraviolet radiation that ionizes the surrounding gas, creating glowing nebulae visible across vast distances. As a galaxy matures, it begins to develop structure. If it has significant angular momentum, inherited from the rotation of the gas cloud from which it formed, it settles into a rotating disk. Within this disk, density waves organize stars and gas into spiral arms, elegant patterns that rotate around the galactic center. Stars form preferentially in these spiral arms, where gas is compressed by the passing density wave. The galaxy takes on the classic spiral form we see in galaxies like our own Milky Way or the nearby Andromeda galaxy. The disk of a spiral galaxy contains young hot blue stars mixed with older, cooler yellow and red stars. Gas lanes trace the spiral arms, visible as dark patches where dust blocks light from stars behind. At the centre lies the bulge, a roughly spherical concentration of older stars, and at the very heart of the bulge lurks a supermassive black hole, containing millions to billions of times the mass of the Sun. This black hole profoundly influences the galaxy's evolution, though in ways that are still not completely understood. Star formation in a mature galaxy is a self-regulating process. Gas collapses to form stars, but the stars themselves affect the gas around them. Massive stars produce powerful winds that push gas away. Supernova explosions inject tremendous energy into the interstellar medium, heating gas and driving it outward in expanding bubbles and shells. This feedback can temporarily suppress star formation in regions around young star clusters, giving the galaxy a breathing, pulsating quality where star formation surges and ebbs over millions of years. The supermassive black hole at a galaxy's centre can dramatically affect its evolution. When gas falls toward the black hole, it forms an accretion disk, heating to millions of degrees and emitting intense radiation across the electromagnetic spectrum. This active galactic nucleus can outshine all the stars in the galaxy combined. The energy released can drive powerful winds and jets that blow gas out of the galaxy entirely, removing the raw material needed for star formation. Many galaxies go through active phases when their central black holes are feeding vigorously, then quiet phases when little material is falling inward and the black hole lies dormant. Galaxies don't evolve in isolation. They're part of a cosmic web, connected by filaments of dark matter and gas to other galaxies nearby. Smaller galaxies fall into larger ones, adding their stars and gas to the growing giant. The Milky Way has consumed dozens of smaller satellite galaxies over its history, and it will consume more in the future. Each merger adds complexity to the galaxy's structure, sometimes triggering bursts of star formation as gas clouds collide and compress, sometimes disrupting the orderly rotation of the disk and scattering stars into less organized orbits. Major mergers, when two galaxies of comparable size collide, are transformative events. The collision unfolds over hundreds of millions of years as the galaxy's gravitational fields interact. Stars almost never collide directly. The distances between stars are so vast that even in a galactic collision, stellar collisions are extraordinarily rare. But the gravitational interactions between the passing galaxies create tidal forces that stretch and distort each galaxy's structure. Long tidal tails of stars and gas stream away from the collision site, some eventually falling back into the merged system, others dispersed into intergalactic space. The gas in colliding galaxies does collide, directly and violently. Giant molecular clouds slam together at speeds of hundreds of kilometers per second, creating shockwaves that compress the gas and trigger intense bursts of star formation. These starburst galaxies can form stars at rates hundreds of times higher than normal galaxies, converting much of their gas into stars within just tens of millions of years. The newly formed massive stars live brief lives and explode as supernovae, creating a cascade of feedback that heats the remaining gas and can drive much of it out of the galaxy entirely. The end result of a major merger is typically an elliptical galaxy. The orderly rotation of the spiral disks is destroyed by the chaotic gravitational interactions of the merger. Stars end up on random orbits, creating a roughly spherical or elliptical distribution rather than a flat disk. Elliptical galaxies contain mostly old stars, appearing yellowish or reddish because they lack the young blue stars that make spiral galaxies appear white or blue. They have little gas left for star formation, having either converted most of their gas into stars during the merger or expelled it through feedback from star formation and active galactic nuclei. Elliptical galaxies represent a kind of middle age or retirement for galaxies. They're massive, sometimes containing trillions of stars, but they're largely quiescent, forming few new stars. The stars within them are aging, slowly converting hydrogen to helium in their cores, gradually dimming as they exhaust their fuel. Over hundreds of billions of years, these stars will die one by one. Low-mass stars will swell into red giants, then shed their outer layers as planetary nebulae, leaving behind white dwarf remnants. Higher-mass stars will explode as supernova, leaving neutron stars, or black holes. As stars die, they return some of their material to the interstellar medium, but much of their mass remains locked in stellar remnants. The galaxy's gas supply dwindles, and with no new gas falling in from outside, star formation gradually ceases. The galaxy grows dimmer as its most luminous stars die and are not replaced. Eventually, in the far future, such a galaxy would consist primarily of white dwarfs, neutron stars, and black holes, the dead remnants of stars that once shone brightly. Some galaxies meet more dramatic ends. In dense galaxy clusters, high-speed collisions and gravitational interactions can tear galaxies apart. Ram pressure stripping occurs when a galaxy moves through the hot intracluster gas that fills the space between galaxies in a cluster. This hot gas, though tenuous, exerts pressure on the cold gas in the moving galaxy, stripping it away like wind pulling leaves from a tree. The galaxy is left with no gas for star formation, rapidly aging as its existing stars evolve and die without being replaced. Galaxies can also be tidally disrupted by close passes to much more massive galaxies. The tidal forces, the difference in gravitational pull between the near and far sides of the smaller galaxy, can be strong enough to overcome the galaxy's self-gravity, pulling it apart into streams of stars that wrap around the larger galaxy. The Milky Way is currently in the process of tidally disrupting the Sagittarius dwarf elliptical galaxy, a small galaxy that passed too close and is now being stretched into a stream of stars encircling our galaxy. In the very long term, over timescales of trillions of years, galaxies face a dark future. The expansion of the universe, driven by dark energy, is accelerating. Galaxy clusters will remain gravitationally bound, but individual clusters will become increasingly isolated from each other as the space between them grows. Within each cluster, galaxies will gradually merge, forming ever larger elliptical galaxies. Eventually, each cluster will merge into a single giant elliptical galaxy containing all the matter that was once in dozens or hundreds of separate galaxies. Even these ultimate galaxies will fade. Star formation will cease entirely as all available gas is either converted into stars or expelled from galaxies. The remaining stars will age and die. White dwarfs will cool, becoming black dwarfs, cold, dark stellar remnants that no longer emit visible light. Neutron stars will radiate away their heat over inconceivable timescales. Black holes will slowly evaporate through Hawking radiation, though this process takes vastly longer than the current age of the universe. 10 to the power of 10, 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 to the power of 10 to 100th power years for a solar mass black hole. Far longer for the supermassive black holes at galaxy centers. The life cycle of galaxies is intimately connected to the larger evolution of the universe itself. In the early universe, galaxies formed rapidly and evolved quickly, building up their stellar populations and establishing their structures. In the current era, galaxies continue to form stars but more sedately, and many have settled into mature configurations. In the far future, galaxy formation will cease as the expanding universe spreads matter too thinly for new gravitational collapses to occur. The galaxies that exist will gradually fade as their stars die and are not replaced. But this distant future is trillions of years away. For now, and for the foreseeable future, galaxies remain vibrant systems. Star formation continues, though at lower rates than in the past. Galaxies merge and interact, transforming themselves in violent collisions that reshape their structures. New observations reveal galaxies at ever greater distances, showing us how they looked when the universe was young, allowing us to piece together the story of how galaxies live and die, how they transform over cosmic time, and how the universe itself evolves through the changes that galaxies undergo as they pass through their long but finite lifespans. How black holes warp time itself. Time is not the constant, uniform flow that our everyday experience suggests. It can stretch, compress, and slow down, depending on the gravitational environment you're in. Nowhere is this more extreme than near a black hole, where gravity becomes so intense that time itself warps in ways that challenge our intuition and transform our understanding of reality. Understanding how black holes affect time means grappling with one of the most profound insights of modern physics, that space and time are not separate, fixed stages on which events unfold, but rather a unified fabric that can be bent, twisted, and stretched by the presence of mass and energy. The foundation for understanding time dilation near black holes comes from Albert Einstein's general theory of relativity, published in 1915. Einstein proposed that what we perceive as gravity is actually the curvature of space-time caused by mass and energy. Massive objects create depressions in the fabric of space-time, much like a bowling ball placed on a stretched rubber sheet creates a depression that affects how nearby marbles roll. This curvature affects not just the paths that objects follow through space, but also the rate at which time passes. The basic principle is that time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, has been confirmed through countless experiments. Atomic clocks placed at different altitudes on Earth tick at measurably different rates. Clocks at sea level run slightly slower than clocks on mountaintops, because they're deeper in Earth's gravitational well. The difference is tiny, only nanoseconds per day, but it's real and measurable. GPS satellites must account for this effect. Without corrections for gravitational time dilation, GPS coordinates would drift by several kilometers per day. Near a black hole, gravitational time dilation becomes extreme. Imagine two observers, one hovering far from a black hole in weak gravity, the other hovering closer to the black hole, where gravity is much stronger. If both observers synchronize their watches and then separate, the watch closer to the black hole will tick more slowly from the distant observer's perspective. This isn't an illusion or a malfunction of the watch. Time genuinely passes more slowly in the stronger gravitational field. The closer you get to a black hole, the more severe this effect becomes. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. This creates one of the most counterintuitive aspects of black holes. If you were to watch someone fall toward a black hole while you remained safely far away, you would see something strange. As the falling person approached the event horizon, they would appear to slow down. Their movements would become sluggish, their signals would take longer to reach you, and their image would become increasingly red-shifted as the light they emit is stretched by the intense gravity. From your distant vantage point, the falling person would never quite seem to cross the event horizon. They would appear to freeze at the boundary, becoming dimmer and redder until they faded from view entirely. This isn't because they stopped falling. From their own perspective, they would cross the event horizon and continue falling inward in a finite amount of time, experiencing nothing unusual at that precise moment. The difference is entirely due to how time flows differently in different gravitational fields. This discrepancy between what the falling observer experiences and what the distant observer sees is one of the most mind-bending aspects of general relativity. Both perspectives are equally valid. The falling observer crosses the event horizon in, say, 10 seconds by their clock, but from the distant observer's perspective, watching that crossing would take infinite time. It would never be complete. This isn't a contradiction, but rather a demonstration that time is not absolute. Different observers in different gravitational fields experience time at different rates. The mathematics describing this time dilation near black holes was first worked out by Carl Schwarzschild in 1916, just months after Einstein published general relativity. Schwarzschild found an exact solution to Einstein's equations describing the spacetime around a non-rotating, spherically symmetric mass, what we now call a Schwarzschild black hole. His solution showed that time dilation increases as you approach the event horizon, located at what's now called the Schwarzschild radius, reaching infinite dilation exactly at the horizon. For a rotating black hole, described by the Kerr solution, found by Roy Kerr in 1963, the situation becomes even more complex. Rotation creates additional effects beyond simple time dilation. The black hole drags spacetime around with it in a process called frame dragging. Close to a rotating black hole, space itself is pulled around in the direction of rotation. You couldn't remain stationary, even if you wanted to. You'd be forced to rotate with the space-time itself. This creates regions like the ergosphere outside the event horizon, where frame dragging is so strong that everything must move in the direction of the black hole's rotation. The warping of time near black holes has practical implications for anything orbiting or falling toward them. Consider material in an accretion disk spiraling into a black hole. Material in the inner portions of the disk, closer to the black hole, experiences stronger time dilation than material farther out. From the perspective of an observer far from the black hole, processes in the inner disk appear to run in slow motion compared to processes in the outer disk. This affects how we observe black holes and interpret the light we receive from matter near them. Time dilation also affects the gravitational redshift of light, escaping from near a black hole. Light climbing out of a gravitational well loses energy, its wavelength stretching toward the red end of the spectrum. This gravitational redshift is intimately connected to time dilation. They're two aspects of the same phenomenon. A photon emitted from close to the event horizon will be dramatically redshifted by the time it reaches a distant observer. If the photon is emitted from the event horizon itself, it would be redshifted infinitely, its energy dropping to zero, another way of understanding why nothing can escape from beyond the horizon. Inside the event horizon, the warping of spacetime becomes even more extreme. In this region, the roles of space and time actually exchange in a sense. Outside the horizon, moving forward in time is inevitable. You cannot choose to move backward in time, but you can choose your direction in space. Inside the horizon, moving toward the singularity at the center becomes as inevitable as moving forward in time outside the horizon. All possible paths lead inward, and reaching the singularity becomes as unavoidable as reaching the next moment in time. The singularity at the center of a black hole represents a place where space-time curvature becomes infinite, and general relativity's equations break down. At the singularity, time itself becomes undefined in the classical sense. This suggests that general relativity is incomplete, that a theory of quantum gravity would be needed to properly describe what happens at and beyond the singularity. String theory, loop quantum gravity, and other approaches to quantum gravity propose different solutions to what occurs at this extreme limit, but none have been confirmed experimentally. Supermassive black holes at the centers of galaxies create fascinating time dilation effects on galactic scales. The black hole at the center of our Milky Way galaxy, called Sagittarius A star, contains about 4 million solar masses. Stars orbiting close to this black hole experience measurable time dilation. A star in a close orbit around Sagittarius A star, coming within a few hundred times the black hole's event horizon radius, would experience time flowing noticeably slower than we experience it here on Earth, 26,000 light-years away. Precise measurements of these stars' orbits by Andrea Ghez and Reinhard Genzel, who shared the 2020 Nobel Prize in Physics for this work, have confirmed general relativity's predictions in this strong gravity regime. Time dilation near black holes has captured popular imagination, featuring prominently in science fiction. The film Interstellar depicted a planet orbiting close to a massive rotating black hole, where time dilation was so extreme that 1 hour on the planet's surface equaled 7 years of time passing elsewhere. While Hollywood took some liberties, the basic physics was sound. Physicist Kip Thorne served as scientific consultant and later published papers about the black hole physics portrayed in the film. Such extreme time dilation is theoretically possible near a rapidly rotating supermassive black hole. Binary black hole systems, where two black holes orbit each other before merging, create incredibly complex space-time geometries. Each black hole warps time in its vicinity, and the combined warping creates regions where time flows at different rates depending on your location relative to the two black holes. As the black holes spiral together and merge, events that produce the gravitational waves detected by LIGO and other observatories, the warping of spacetime becomes dynamical, with gravitational waves carrying information about how spacetime is oscillating and rippling during this violent event. The connection between time dilation and energy offers another perspective on these phenomena. According to general relativity, gravitational fields contain energy. A clock deep in a gravitational well, where time runs slowly, can be thought of as having less energy than a clock far from any gravitational source. The gravitational redshift of light, the loss of energy as light climbs out of a gravitational well, reflects this energy difference between different regions of curved spacetime. Black holes also raise profound questions about the nature of time itself. Some interpretations of quantum mechanics and general relativity suggest that time might not be fundamental, but rather an emergent property of more basic physical processes. Black holes, where classical notions of time break down at the singularity, might provide clues about the true nature of time. The information paradox, the question of what happens to information that falls into a black hole, connects to deep questions about time, entropy, and the quantum nature of spacetime. Hawking radiation, predicted by Stephen Hawking in 1974, introduces another connection between black holes and time. Quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate over extremely long timescales. This process involves virtual particle pairs appearing near the horizon, with one particle falling in while the other escapes. The evaporation means black holes have a finite lifetime, and it connects quantum mechanics, gravity, and thermodynamics in ways that hint at a deeper theory unifying these domains. The warping of time near black holes is not science fiction, but established physics, confirmed through observations and experiments. Every time LIGO detects gravitational waves from merging black holes, it's detecting ripples in spacetime that carry information about how dramatically spacetime, and therefore time itself, was warped during the merger. Every observation of matter orbiting near black holes, every measurement of gravitational redshift, every test of general relativity in strong gravitational fields, confirms that time is not absolute, but is woven into the fabric of spacetime, susceptible to warping and stretching by mass and energy, reaching its most extreme manifestation near black holes, where the flow of time slows to a crawl, and ultimately, at the event horizon, appears to stop entirely from the perspective of distant observers watching the inexorable pull of gravity on the fabric of reality itself. How we find planets around other stars. For most of human history, planets were only known to exist in our own solar system. Mercury, Venus, Mars, Jupiter, and Saturn were visible to the naked eye, and with telescopes came the discoveries of Uranus and Neptune. But beyond our solar system, despite billions upon billions of stars filling the galaxy, no one had ever confirmed the existence of even a single planet orbiting another star. The problem wasn't that exoplanets, planets around other stars, didn't exist. The problem was that they're extraordinarily difficult to detect. A planet is tiny compared to its star, produces no light of its own, and sits right next to a brilliant star that outshines it completely. Trying to see a planet next to its star is like trying to spot a firefly hovering next to a searchlight from hundreds of miles away. The first confirmed exoplanet around a Sun-like star was discovered in 1995 by Michel Mayor and Didier Queloz, who shared the Nobel Prize in Physics in 2019 for this groundbreaking work. They didn't actually see the planet. Instead, they detected its presence indirectly by observing how it affected its parent star. This indirect approach has proven to be the key to finding exoplanets, and astronomers have developed several clever techniques that reveal planets without ever actually imaging them directly. The method Mayer and Queloz used is called the radial velocity technique, sometimes known as the Doppler wobble method. The basic principle relies on the fact that a planet doesn't simply orbit its star. Rather, both the planet and the star orbit their common center of mass. Imagine two ice skaters holding hands and spinning around. If one skater is much heavier than the other, the heavy skater barely moves, while the light skater whips around in a large circle. But the heavy skater does move slightly, wobbling around their common center as they spin. The same happens with stars and planets. Jupiter, the most massive planet in our solar system, causes the Sun to wobble slightly as both orbit their common center of mass. The Sun's wobble is small. It shifts back and forth by only about 13 meters per second, roughly the speed of a bicycle. But this wobble is detectable. As the star moves toward Earth, its light gets slightly blue shifted, compressed to shorter wavelengths. As it moves away, the light gets red shifted, stretched to longer wavelengths. By measuring these tiny shifts in the star's spectrum with extremely precise instruments, astronomers can detect the wobble and infer that a planet must be causing it. The planet Mayer and Queloz discovered, orbiting a star called 51 Pegasi, created a much larger wobble than Jupiter creates in our Sun, because this planet is both massive and very close to its star. It completes an orbit in just over 4 days, compared to Jupiter's 12-year orbit. The close proximity and short period make the wobble more pronounced and easier to detect. This planet, later named Dimidium, shocked astronomers because it's a gas giant similar to Jupiter, but orbiting closer to its star than Mercury orbits our Sun. Before this discovery, most astronomers assumed that giant planets could only form far from their stars, where temperatures were cold enough for ice to exist. The discovery of hot Jupiters revolutionized our understanding of how planetary systems form and evolve. The radial velocity method works best for finding massive planets close to their stars because these create the largest wobbles. Small planets like Earth create wobbles so tiny that they're difficult to detect even with the best current instruments. A planet similar to Earth orbiting a Sun-like star at Earth's distance would cause a wobble of less than 1 meter per second, slower than walking pace. Detecting such minute velocity changes requires incredibly stable spectrographs and careful corrections for other sources of stellar variability, like star spots and convection in the star's atmosphere. The second major technique for finding exoplanets is the transit method, which has discovered more exoplanets than any other technique. A transit occurs when a planet passes directly in front of its star, as seen from Earth, blocking a tiny fraction of the star's light. For a Jupiter-sized planet transiting a Sun-like star, the star's brightness drops by about 1%. A small change, but definitely measurable with precise photometry. For an Earth-sized planet, the drop is much smaller, only about 1/100th of 1%, but still detectable with sufficiently sensitive instruments. The Kepler Space Telescope, launched by NASA in 2009, was specifically designed to detect transits. Kepler monitored the brightness of more than 150,000 stars continuously for over 4 years, searching for the telltale dips in brightness that indicates a planet passing in front of its star. The mission was spectacularly successful, discovering thousands of exoplanets and showing that planets are common. Most stars have at least one planet, and many have multiple planets. Transit observations provide information that radial velocity measurements cannot. The depth of the transit, how much the star's brightness decreases, reveals the planet's size. A bigger planet blocks more light, creating a deeper transit. The duration of the transit reveals information about the planet's orbital distance and the star's size. By combining transit observations with radial velocity measurements, astronomers can determine both the planet's size and its mass, which allows them to calculate its density and infer what it might be made of. A low-density planet is probably a gas giant like Jupiter. A high-density planet is likely rocky like Earth. A medium density might indicate a water world or a planet with a thick atmosphere. The transit method has limitations. It only works for planets whose orbits happen to be aligned edge-on from Earth's perspective. If a planetary system is tilted so that planets pass above or below the star rather than directly in front of it, no transits occur, and the planets remain undetectable by this method. Statistically, only a small fraction of planets are oriented correctly for transits to be visible from Earth. For a planet at Earth's distance from a Sun-like star, the probability of correct alignment is less than 1%. Despite this limitation, Kepler's strategy of monitoring thousands of stars simultaneously meant that even with low individual probabilities, many planets were discovered. Direct imaging represents the most straightforward approach, actually taking a picture of the planet next to its star, but it's also the most technically challenging. The problem is the enormous brightness difference. A Sun-like star is typically 10 billion times brighter than a Jupiter-like planet at visible wavelengths, and the planet sits right next to the star in the sky. Special techniques are required to block the star's light and reveal the faint planet. Coronagraphs, which create an artificial eclipse by placing a mask over the star, and star shades, which fly separately from the telescope and block the star's light before it enters the telescope, both enable direct imaging. Direct imaging works best for young, massive planets that are far from their stars. Young planets are still hot from their formation, glowing brightly in infrared light, making the contrast ratio more favorable. Planets farther from their stars are more separated in angle, making them easier to distinguish from the star's glare. Several dozen planets have been directly imaged, mostly young gas giants orbiting at large distances from their stars. These planets appear as faint dots of light in images taken with large, ground-based telescopes equipped with adaptive optics systems that correct for atmospheric blurring. Gravitational microlensing provides another method for detecting exoplanets, particularly useful for finding planets at large distances from Earth and planets far from their host stars. The technique relies on general relativity. When one star passes almost directly in front of a more distant background star from Earth's perspective, the foreground star's gravity acts as a lens, bending and focusing the background star's light. This creates a temporary brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence. Microlensing events are rare and unpredictable. You can't choose to observe a particular star and wait for a microlensing event. Instead, astronomers monitor millions of stars in dense stellar regions, like the galactic bulge, waiting for events to occur. When an event happens, it's unique. The same foreground and background star will never align again in human timescales. This makes follow-up observations challenging, but the method has discovered several dozen planets and is particularly good at finding planets in the outer reaches of planetary systems where other methods struggle. Astrometry measures the precise position of a star in the sky over time. If a planet is present, the star wobbles back and forth on the sky, shifting position slightly as both star and planet orbit their common center of mass. This is similar to the radial velocity method, but measures the wobble in position rather than in velocity. The wobble is extremely small. For Jupiter orbiting the Sun, as seen from a distance of 10 light-years, the wobble would be about half a millisecond, roughly equivalent to measuring the width of a human hair from a distance of 200 miles. The European Space Agency's Gaia mission, launched in 2013, is measuring the positions of over 1 billion stars with unprecedented precision, and it's beginning to detect the astrometric wobbles caused by giant planets. As Gaia continues its mission and accumulates more data, it will discover planets through astrometry and provide three-dimensional orbital information for many planets discovered by other methods. Each detection method has biases. It favours finding certain types of planets over others. Radial velocity finds massive planets close to their stars. Transits find planets of all masses, but only those aligned edge-on. Direct imaging finds young massive planets far from their stars. Microlensing finds planets at all distances but works best for planets far from their stars. By using multiple methods, astronomers build a more complete picture of the diversity of planetary systems. The combination of techniques has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury. Super-Earths, planets larger than Earth but smaller than Neptune, appear to be extremely common, yet don't exist in our solar system. Some systems have planets in extremely compact orbits, with multiple planets packed closer to their star than Mercury is to our Sun. Other systems have planets on highly eccentric orbits, stretching from close in to far out in elongated ellipses. Some planets orbit binary stars, experiencing sunsets with two suns like Luke Skywalker's home planet Tatooine in Star Wars. The atmospheres of exoplanets can be studied through transit spectroscopy. When a planet transits its star, some starlight filters through the planet's atmosphere on its way to Earth. Different molecules in the atmosphere absorb light at specific wavelengths, creating an absorption spectrum that reveals the atmospheric composition. Astronomers have detected water vapor, methane, carbon dioxide, and other molecules in exoplanet atmospheres. The James Webb Space Telescope, launched in 2021, is revolutionizing this field with its ability to detect even fainter spectral signatures and characterize the atmospheres of smaller, potentially habitable planets. The search for Earth-like planets in habitable zones, the region around a star where temperatures allow liquid water to exist on a planet's surface, drives much exoplanet research. Kepler discovered several candidates, including Kepler 452b, a planet slightly larger than Earth orbiting a Sun-like star at a distance where temperatures might support liquid water. Whether any of these planets actually harbour life remains unknown, but the discovery that Earth-sized planets in habitable zones exist at all is profound. We're no longer wondering whether such planets exist, but rather whether any of them host life. Future missions will improve our ability to find and characterize Earth-like planets. The Nancy Grace Roman Space Telescope will use microlensing and direct imaging to find planets. Ground-based extremely large telescopes currently under construction will directly image planets and study their atmospheres in detail. Proposed missions like the Habitable Worlds Observatory aim to directly image dozens of Earth-like planets and search their atmospheres for biosignatures, gases like oxygen and methane that might indicate the presence of life. In less than 3 decades, exoplanet science has progressed from the first tentative discovery to finding thousands of planets, characterizing their properties, studying their atmospheres, and identifying candidates that might harbor life. The methods astronomers developed to overcome the challenge of finding tiny, faint planets next to brilliant stars have succeeded beyond initial expectations, revealing that planets are not rare accidents but common outcomes of star formation. That our solar system is just one example among billions of planetary systems filling the galaxy, and that the question of whether we're alone in the universe might finally be answerable through observations of the atmospheres of distant worlds orbiting alien suns. How planets form from dust. In the beginning, there were no planets, no Earth, no Jupiter, no rocky worlds or gas giants, just vast clouds of gas and dust drifting through the galaxy. Yet from these diffuse, seemingly formless clouds, gravity and physics conspired to build the solid worlds we see today. Understanding how planets form from dust means understanding one of nature's most remarkable construction projects, a process that transforms microscopic particles floating in space into spheres thousands of miles across, complete with cores, mantles, atmospheres, and sometimes even moons. The story begins with a molecular cloud, a cold, dark region of space, filled primarily with hydrogen and helium gas, left over from the Big Bang, mixed with about 1% heavier elements and dust particles created in previous generations of stars. These dust grains are tiny, typically only a fraction of a micrometer across, smaller than bacteria. They're composed of silicates, rocky minerals similar to sand, and sometimes ices of water, carbon dioxide, or methane, depending on the temperature of the cloud. Something disturbs the cloud. Perhaps a nearby star explodes as a supernova, sending a shockwave rippling through space. Perhaps the cloud passes through a spiral arm of the galaxy where gas is compressed. Whatever the trigger, a region of the cloud begins to collapse under its own gravity. As it collapses, it spins faster due to conservation of angular momentum. The same principle that makes a figure skater spin faster when pulling their arms inward. The collapsing cloud flattens into a disk, a swirling pancake of gas and dust with a growing concentration of mass at the center. This is a protoplanetary disk, and it's where planets will form. The center grows hotter and denser as material falls inward, eventually becoming a protostar that will ignite nuclear fusion and become a star. But the disk surrounding the star contains enough material to build an entire family of planets. In the disk, dust particles drift through the gas, occasionally bumping into each other. When they collide gently, they can stick together. The sticking happens through several mechanisms. Sometimes electrostatic forces, essentially static electricity, cause particles to cling to each other. Sometimes molecular forces, similar to the forces that make wet sand stick together, bind the particles. Ice coatings on particles in the colder outer regions of the disk act like glue, making particles particularly sticky. These gentle collisions build larger particles. A dust grain collides with another, and they stick, forming a slightly larger grain. This larger grain has a bigger cross-section, making it more likely to encounter and stick to other grains. Slowly, grain by grain, the particles grow from microscopic dust into pebbles, then into rocks, then into boulders. This process, called accretion, is slow at first but accelerates as particles grow larger. The growing clumps begin to settle toward the midplane of the disk, the thin central plane where the density is highest. Larger particles settle faster than smaller ones because they're less buffeted by gas turbulence. The midplane becomes a dense layer of solid material embedded in the gas disk, creating favorable conditions for further growth. Particles collide more frequently in this dense environment, accelerating the growth process. When the solid objects reach sizes of about a kilometer across, they're called planetesimals. These are the building blocks of planets, and reaching this size represents a critical milestone. Objects this large have enough gravity to begin attracting nearby material, rather than relying solely on chance collisions. Their gravity pulls in smaller rocks and dust, causing them to grow faster. The biggest planetesimals grow the fastest because their stronger gravity allows them to clear out larger regions of the disk, creating what astronomers call runaway growth. The protoplanetary disk is a chaotic place. Planetesimals don't just grow peacefully, they also collide with each other. Some collisions are gentle enough that the objects merge, creating larger bodies. But other collisions are violent, shattering one or both objects into fragments. Whether a collision leads to growth or destruction depends on the relative velocities. Slow collisions, at a few meters per second, tend to result in sticking and growth. Fast collisions at kilometers per second tend to be destructive. Over time, certain planetesimals become dominant, growing larger than their neighbors. These become planetary embryos, objects roughly the size of our Moon or Mars, hundreds to thousands of kilometers across. The largest embryos in each region of the disk sweep up most of the available material in their vicinity, clearing out their orbital zones. When two similarly sized embryos eventually collide, the impact can be cataclysmic, melting both objects and creating a larger planet from the merged material. The composition of forming planets depends on their distance from the star. Close to the star, temperatures are high, hot enough that volatile materials like water, methane, and ammonia can't condense into solid form. Only materials with high melting points, metals and rocky minerals, can exist as solids. This is why the inner planets of our solar system, Mercury, Venus, Earth, and Mars, are rocky worlds made of iron and silicates. Farther from the star, beyond a boundary called the snow line or ice line, temperatures are cold enough for water to freeze into ice. This fundamentally changes planet formation. Because ice is abundant, there's simply more solid material available when you include ice along with rock and metal. The snow line in our solar system was located somewhere around where the asteroid belt is today, between Mars and Jupiter. Beyond the snow line, planetary embryos could grow much larger because more solid material was available. When an embryo grew to roughly 10 times Earth's mass, something dramatic happened. Its gravity became strong enough to capture gas directly from the surrounding disk. Hydrogen and helium, the most abundant elements in the disk, began falling onto the growing planet. Once this process started, it ran away rapidly. The planet's gravity pulled in more gas, which made it more massive, which increased its gravity, which allowed it to pull in even more gas. This runaway gas accretion created the gas giant planets, Jupiter and Saturn, in our solar system. These worlds are mostly hydrogen and helium, like miniature stars, with relatively small rocky and icy cores buried beneath thousands of kilometers of gas. Jupiter grew so large and so quickly that it dominated its region of the solar system, its powerful gravity stirring up the asteroid belt and preventing the material there from ever forming a planet. Uranus and Neptune, the ice giants, also formed beyond the snow line, but grew more slowly. They captured some gas from the disk, but not as much as Jupiter and Saturn, possibly because the gas in their region was less dense or because the disk dispersed before they could grow large enough to undergo runaway gas accretion. These planets are dominated by water, methane, and ammonia ices, rather than hydrogen and helium gas. The protoplanetary disk doesn't last forever. The young star at the center begins generating powerful stellar winds and intense radiation. Over a few million years, this wind sweeps away the remaining gas in the disk, ending the era of planet formation from gas accretion. Any planets that hadn't finished growing could no longer capture gas from the disk. This probably explains why Mars is so small. It formed in a region where less material was available, and the gas dispersed before it could grow much larger. Even after the gas disk disperses, planet formation continues through collisions between the remaining planetesimals and planetary embryos. This era, called the late heavy bombardment or giant impact phase, was violent. Computer simulations suggest that the inner solar system initially formed several more planetary embryos than the 4 terrestrial planets we see today. These embryos had chaotic, crossing orbits, and they repeatedly collided over tens of millions of years. Eventually, through this sequence of giant impacts, the embryos merged into the 4 stable planets, Mercury, Venus, Earth, and Mars, we observe today. Earth's moon likely formed during one of these giant impacts. About 4.5 billion years ago, a Mars-sized object struck the young Earth at an oblique angle. The impact vaporized both the impactor's outer layers and a large portion of Earth's mantle, ejecting an enormous amount of material into orbit around Earth. This material, a mixture of vaporized rock and molten droplets, quickly coalesced into the Moon. The Moon's composition, which closely matches Earth's mantle but lacks iron from Earth's core, supports this giant impact origin. The timing of planet formation varies. In our solar system, Jupiter formed within a few million years, fast enough to capture gas before the disk dispersed. The terrestrial planets took longer, perhaps tens of millions of years to reach their final sizes. The final giant impacts on Earth, including the moon-forming impact, occurred somewhere around 50 to 100 million years after the disk first started collapsing. This might seem long, but it's less than 1% of Earth's current age. Planet formation is remarkably quick on astronomical timescales. Not all the material in the protoplanetary disk becomes part of planets. Some planetesimals survive in stable regions where planets didn't form. The asteroid belt contains remnants of planetesimals that never accreted into a planet, stirred up and prevented from merging by Jupiter's gravitational influence. The Kuiper belt beyond Neptune and the more distant Oort cloud contain frozen planetesimals preserved from the solar system's formation, rich in ices that couldn't exist in the warmer inner regions. Observations of protoplanetary disks around young stars show this process happening in real time. The Atacama Large Millimeter Array in Chile has captured stunning images of disks with gaps and rings, structures created by forming planets as they clear out their orbital zones. Some disks show spiral patterns caused by gravitational perturbations from massive planets still embedded in the disk. These observations confirm that planet formation is common and that the process we see in our solar system occurs around most stars. Planet formation doesn't always produce systems like ours. Exoplanet discoveries have revealed hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. These planets must have formed farther out beyond the snow line, where ice could exist, then migrated inward through gravitational interactions with the disk or with other planets. Some planetary systems are extremely compact, with multiple planets orbiting closer to their star than Mercury. Others have planets on highly elliptical orbits, unlike the nearly circular orbits in our solar system. From microscopic dust grains to planet-sized worlds represents a journey across more than 10 orders of magnitude in size, a factor of tens of billions. The process transforms diffuse material spread across millions of miles into concentrated spheres where gravity compresses matter so intensely that planetary interiors melt and differentiate into layers, where atmospheres form and weather patterns emerge, and where, at least on one planet we know of, conditions become suitable for life to arise. All of this complexity, all of this structure, emerges from nothing more than dust, gas, gravity, and time, following the laws of physics that govern how matter behaves when concentrated by the inexorable pull of gravity in the rotating disk around a young star.